Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. So today I'll be discussing how to analyze a propped cantilever beam which is shown in the figure and how to draw the shear force and bending moment diagram for this particular numerical. So here you can see here it is a propped cantilever beam wherein at A it is a fixed end and at B it is having a roller support. The total span of the propped cantilever beam is 3 meters and throughout you have a UDL here and the UDL magnitude is given as 10 kilonewton per meter and you also have a concentrated load of 5 kilonewton which is a center concentrated load which is equally distributed from the either of the two side of a support. Now in order to analyze the given cantilever, that is a propped cantilever beam, the first and foremost step is that we are going to do the elastic load diagram due to the reaction at point B. So that is RB. So first and foremost thing is that step 1 it is a load diagram that is elastic load diagram due to VB, that is vertical reaction at B. Since it is a roller support, so you will be having one reaction in the vertical direction, so therefore it is VB. So here I just represent the vertical reaction at B as VB. So here you will be having the fixed support then at A, and this is equal to 3 meters. Only I am going to concentrate here with reference to the support reaction at B, that is VB. Other than that, I am going to only concentrate on VB other than any other loaded cases. So first VB, the moment about A I am supposed to consider. So moment about A I am supposed to consider due to VB. So here the moment are basically defined as load into perpendicular distance. So load is VB, perpendicular distance is 3 meters. So VB into 3, it is the moment along A. So here again I'll write the base diagram. So VB into 3, it is going along the anti-clockwise direction. How it is anti-clockwise? So here go along the loaded direction and touch the point A. Go along the loaded direction and touch the point A. It is anti-clockwise direction. So as per our sign convention, anti-clockwise right hand side it is taken as positive. Anti-clockwise moment right hand side is taken as positive. Clockwise right hand side is taken as negative, and the same will be replicated with a reverse sign convention with when it is taken from left hand side. So it is anti-clockwise right hand side, so it is taken to be as positive. So positive value will be taken above the baseline, so that value will be equal to 3 times of VB, that is VB into 3, so it is 3 VB. Since it is the concentrated load, so the variation is triangular variation. So it is a triangular variation. So I'll mark this as positive, and this is equal to 3 meters, and this is equal to our 3 meters. Now with reference to this, I just mark a point here. I just consider this as a centroidal point. So wherein this is a triangle wherein the centroid of a triangle will be 1/3 and 2/3 from the reference direction based on the shorter on the longer span. So this is the longer side of the centroid, so it will be 2/3 of the base. So base is equal to 3 meters, so 2/3 of the span. So 2/3 of span, I just consider this as equal to x1. So x1 will be equal to 2 by 3 of 3. So this will be equal to one third of the base distance. So this will be from the A side. So this is from the B side. So here this is with reference to the free body diagram, the elastic diagram with reference to the support reaction at B. Now next, taking the loaded cases. So I am going to consider the different loaded cases. So there are two loads here. You can observe one is UDL of 10 kilonewton per meter, and another is the concentrated load which is 5 kilonewton, which is a center concentrated load. Now instead of considering both at a time, it will be leading to confusion. So second load I just consider, instead of two I just consider one by one. So I just consider the load UDL throughout. First I'll consider that one by one. Now it is UDL I have considered 10 kilonewton per meter. Don't be in a mindset that I have not considered the VB here, because only I am concentrating on the load condition here, because I am representing the elastic load diagram here. So this is the elastic load diagram, due to UDL. So this is the elastic load diagram due to UDL. So here I need to consider what is the moment acting about point A. So it is 10 is there. So the distance is 3 meters. So because it is throughout, it is distributed. So 10 into 3 into 3 by 2. So 10 into 3 into 3 by 2. It is acting along downward direction. Go along the downward direction and touch the point A. It is clockwise. Go along this 10. Touch the point A. It is clockwise. So we are going from right to left. So we are going to take right hand side sign convention. So right hand side sign convention, clockwise is considered to be as negative. So I am going to consider the moment diagram in the below the baseline, since it is negative. So it is magnitude is 10 into 3 into 3 by 2. So load into total distance into the centroidal distance. So it is the variation is parabolic. So I am going to represent this as a curved structure with a negative variation. So it is a curved structure with a negative variation. Now again I need to mark this as a centroidal location point. So here I just consider this as x2. So here as we all know that for the triangle, it will be either 1/3 or 2/3 of the base distance. So depending upon which side we are going to take. But here it will be equal to 1/4 or 3/4 of the base distance. So here it is a longer side. So therefore it is 3/4 of base distance. So base distance is 3 meters, means the overall span where the load is distributed, it is 3 meters. So x2 will be 3/4 of 3. It comes on to be 2.25 meters. So this is from point B. So this is the centroidal distance. So next, last one, we are left out with the elastic load diagram for due to the action of load of 5 kilonewton. Due to the action of load of 5 kilonewton. So here step 3. So here you have the elastic load diagram. So you have elastic load diagram at due to 5 kilonewton. So here only I am going to concentrate on the load of 5 kilonewton, which is a center concentrated load. 5 kilonewton, here it is 1.5 and 1.5 meters. So here it is 1.5 and 1.5 meters. So now this is A and this is B, and this is the point where it is equal to C. Now I am going to consider this elastic load diagram due to 5 kilonewton with reference to point A. So therefore the moment I am going to consider with reference to point A itself, so moment is equal to force into perpendicular distance. So force acting is 5 kilonewton, perpendicular distance is 1.5. So 5 into 1.5, go along this force and touch the point A. So it is clockwise. So clockwise right side it is again negative. So 5 into 1.5. So here this is the point of consideration. So it is a triangular variation. Since it is a concentrated load, it is a triangular variation. So now again I want the centroid of this point. I know the centroid of this point from here to here, it is 2/3 of the base distance. Since the base distance is 1.5 meters, so 2/3 of the base distance, but I need from point B. So the point B distance is again 1.5 meters. So this will be equal to this 1.5 plus this distance is equal to 2/3 of the base distance. So 1.5 plus 2 by 3 of 1.5 will be equal to the x3 value. So it comes on to be equal to 2.5 meters. So it comes on to be equal to 2.5 meters. So here this is the value of x3. Now as the deflection at a proper cantilever point, it is 0. So the next step is I am going to apply the first compatibility equation. So step 4, we are going to apply the first equation of compatibility. First compatibility equation I am going to apply. So here in case of first compatibility equation, I am going to take the equation as it is equal to P1 x1 plus P2 x2 plus P3 x3 equal to 0, where P1, P2 and P3 represents the areas of the individual elastic load diagram which we have represented in our step 1, 2 and 3, and x1, x2, x3 represents the centroidal distance of the individual elastic load diagram. So here P1, so if I just go to the step 1, so P1 is for this elastic load diagram. So P1 is equal to area of this overall triangle. So it is half into base into height. So half into base is 3 meters. So height is 3 times of VB. So here half into base is 3 into 3 times of VB into the centroidal distance is x1. So x1 here I have 2/3 of 3, because from B itself we are going to take the convention. So therefore why? Because we know that the deflection for a proper point it is 0. So therefore proper point is equal to B. So therefore from B itself we are going to take the distance of the centroid. So it is equal to x1 equal to 2/3 of 3. So it is 2 by 3 of 3, it comes on to be equal to 2. So next P2 x2. So with reference to the step 2 here, if you can see here step 2 here, it is the parabolic variation. So area of parabola for P2 is 1 by 3 of base into height. So for triangle it is half into base into height. For parabola it is 1/3 of base is 3 meters, height is this distance. So height is this distance. So it comes on to be 10 into 3 into 3 by 2, it comes on to be equal to 45. So 45. So x2 is 2.25. So it is negative variation. So it is minus 1 by 3 of 3 into base into height. Height is 45. So into x2 is equal to 2.25. Next again you have the third elastic load diagram here, where P3 is for area for this triangle. So area of this triangle is equal to half into base distance is 1.5 into height is 5 into 1.5. So it is 7.5. So it is 7.5 into x3 distances from B till this centroid. So we have got it as 2.5. So we have got it as 2.5. So it is a negative value because it is a negative variation. Equate this to 0. Why I am equating this to 0? Because the deflection at the proper point is equal to 0. So therefore I have taken it equal to 0. So therefore after solving all this, we'll get one equation. So after getting that equation, so I can solve for the value of VB. So VB I'll get it as equal to 12.8 kilonewton. So VB I'll get it as equal to 12.8 kilonewton. So now after getting this VB value, so I need to again concentrate on other unknowns. I need to concentrate on other unknowns, wherein for that unknowns that is VA, and then one more is MB. So you can just observe here. So this is the proper point of the cantilever. So this is the proper point of the cantilever. So this is the one unknown VB, and this is one unknown VA, and here you have horizontal HA, and this is the MA. So this is MA. So here the total number of unknowns are 4. That is HA, MA, VA and VB. So here HA, you don't have any horizontal forces here. So automatically HA is equal to 0. Now I have got this is equal to 0. So now I have got the value of VB. So now the pending is VA and MA. So in the VA, I can get by using the horizontal equilibrium condition. I can use the horizontal equilibrium condition, that is summation of all the vertical forces is equal to 0. So it is VA plus VB is equal to 0. So here VA plus VB, summation of all the upward forces is equal to summation of all the downward forces. So here VA plus VB is equal to the upward force is equal to VA plus VB, downward force is 5, and 10 you have UDL. Convert the 10 into point load. How you convert? So 10 into the total distance acting here is 3 meters. So 10 into 3. So 5 plus 10 into 3. So this will be the total value. You know the value of VB. So substitute and get the value of VA. So VA will be equal to the 22.2 kilonewton. So VA will be equal to 22.2 kilonewton, and VB it is equal to 12.8 kilonewton. Now after getting this value, the last unknown is that you are supposed to calculate for MA. Now we need to calculate for MA. So here I need to get the value of MA. So I need to put the moment reference point about point A itself. So taking the reference point about point A. So here I have the load here. Once again I am just telling you, I have the load of 10 kilonewton per meter, and this is 5 kilonewton, and this is total is 1.5 and 1.5 meters. Now if I want to apply the moment about A, summation of all the moment about A in the equilibrium situation is equal to 0. With that condition, if I am applying, so VB starting from B, so VB into the distance is 3 meters. So it is anti-clockwise, so it is negative. So minus VB into 3. Next phi is there, and the distance is 1.5 clockwise. So plus phi into 1.5, and then again I have UDL. So load into distance into centroid. So load is 10, distance is 3, centroid is half of the distance, so 3 by 2. So it is again go along this direction, touch the point A, it is clockwise, so it is considered to be as positive. And again with all this, one more I have, that is MA, which is acting in anti-clockwise direction. So minus MA equal to 0, equal to 0. So therefore, upon all this simplification, I get the value of MA equal to 14.1 kilonewton meter. So this 14.1 kilonewton meter I will get the value. So upon all the simplification, so now we are supposed to do the calculation for shear force and bending moment. Now for the shear force and bending moment substitution, once again I just put the once again I need to put this diagram. So here this is VB, so this is here MA and this is VA. So here it is equal to 10 kilonewton per meter, and this is 5 kilonewton, and this is 1.5 meter and 1.5 meter. So shear force at B, I just take shear force at B, it is equal to upward, before that I just write the sign convention, left hand side, right hand side. So here left hand side upward reaction it is positive, downward reaction it is negative, right hand side upward negative, downward positive. So with this sign convention if I want to proceed, so shear force from right side I just start, upward it is VB I have, so upward it is negative, so minus VB, so minus 12.8 kilonewton. Next at point C I have, so at point C it is minus VB plus 10 into the distance acting from here to here, it is 1.5, and then plus at that point I have 5. So the total will be VB, I know it as minus 12.8 plus 10 into 1.5 plus 5. So here total value of the moment about point C, it is equal to 7.2. So it is equal to 7.2. Next shear force at A, shear force at A, so it is equal to VB minus VB minus VB plus 10 into 3. So total is 10 acting throughout, so it is 10 into the distance is 3, and then plus 5, so plus 5, so it comes on to be 22.2 kilonewton. So this is the shear force for the overall thing. So here for plotting the shear force diagram, it is 12.8 here, and then this is 22.2. Now this is 5 kilonewton, so 5, so this is 7.2, so this becomes 2.2, and then again here it will be 12.8. So this 7.2 and 2.2, it is due to this total combination. Why? Because 7.2 is total, so 5 kilonewton per meter it is the concentrated load it is acting. So if I deduct that, the total will be 2.2, so the, which is due to UDL. So this is how I am going to represent this shear force and shear force diagram. So next, coming on to the bending moment diagram. So bending moment at point B. So if I just take the bending moment diagram, so this is the sketch. If I just represent, if I represent the sketch here, I just take the sketch like this here. So the bending moment diagram at B. So bending moment at B, it is equal to 0, because beyond this you don't have any other point. So bending moment. Next, bending moment at C, it is equal to VB into 1.5. So anti-clockwise right side it is negative, sorry, anti-clockwise right side it is positive. If I just take the sign conventions, left hand side and right hand side, so left hand side clockwise it is positive, anti-clockwise it is negative, right hand side clockwise it is negative, anti-clockwise it is positive. So here it is anti-clockwise right hand side, so it is considered to be as, it is considered to be as positive. So next, bending moment at point A. So bending moment at point A is VB into 3, VB into 3. So here one more thing I just forgot here, VB into 1.5 is there. Upon that I have 10 into 1.5 into 1.5 by 2, which is due to this UDL. So it is clockwise right side, hence it is negative. So clockwise right side, hence it is negative. So now you at point A it is VB into 3. So VB into 3 you have, and then minus 5 into 1.5 minus 10 into 3 into 3 by 2. So this is the total. Again I have minus MA. So again I have minus MA. So the total value is equal to minus MA, that is 14.1 kilonewton meter, which I have got due to A. So this is the bending moment diagram. Here you can just represent like this. So it is the parabolic variation here, and then 0 here. This is the parabolic variation which I have got at point C 7.95 kilonewton meter, and this is the point of contraflexure, and this is point of contraflexure. If I just take this as equal to y, if I just take equal to y, so the point of contraflexure from this point it is equal to minus 14.1, that is equal to minus MA plus VA into y minus 10 into y by 2 equate that to 0. So that will be equal to, if I just substitute this value, minus 5y square equal to 0. So upon that simplification, y I get as 0.77 meters. So this is how we can represent the point of contraflexure. So point of contraflexure, it is a point where the bending moment changes its sign convention. Thank you for watching. Please like, share and subscribe the video. Thank you.